I think we are live already. So please do the honors, Crisia, and you can
All right,
introduce our
so good
speaker.
afternoon. All right, good afternoon, everyone. Welcome to this week's Quantum Ladder seminar, which is an experimental seminar with Andreij Gadelha, who is going to talk about twistor bilayer graphene, how to observe localized phenomena in that. So thank you very much for accepting your invitation, Andrei. The stage is yours. Feel free to start.
Thank you, Crisia, and thank you, Adrian, for the opportunity. Hello, everyone. My name is Andreij Gadelha. I am from Brazil, so I work at the Laboratory of Nanospectroscopy in UFMG, Brazil. Okay, and I will talk about our latest work, which was published in Nature, which is localization phenomena in the magic material. So if you are interested in my work, I show here some web links that you can check it out. And I'd like to tell you a little words about my education. So I did my bachelor in physics at the Federal University of Ceará. So Ceará is located in the northeast part of Brazil. And I did it under the supervision of professors Eduardo B. de Barros and Josué Mendes Filho. So I moved to the southeast part of Brazil, in a state called Minas Gerais. And here I did my master and PhD in physics at the Federal University of Minas Gerais, under the supervision of Professor Leonardo Campos. And here I investigated some unconventional photo detectors. I developed some new architectures for memory devices that can store data for a longer time and has alternative functionalities. And I also worked, I can say, in the frontier between art and science. So I don't know if you guys are familiar with this kind of picture. So this is a famous sculpture of the famous sculptor Aleijadinho in Ouro Preto, Minas Gerais. And he made this sculpture from soapstone. Okay, from soapstone we can get talc, which is a layered material. And I developed some nanocapacitors of it, which can generate quantum light and also control it. I had some awards on my PhD, like an article on the Brazilian Materials Research Society, also a report on the local UFMG radio station, and honorable mention in CAPES and UFMG Physics Awards. And for the past 2 years, I did a postdoc at the Laboratory of Nanospectroscopy with professors Aldo and Luis Gustavo. And here we made this project, which was published on the Nature cover. So this was a great honor and conquer for us, and we draw the attention from the Brazilian media. And now I'm doing a postdoc in multimodal near field with Professor Marcos Rasco at the University of Colorado, okay? But I'm working remotely right now. And before I get to our data and our results, I'd like to contextualize about two main nanotechnology paths, which here I exposed to, the nanomanipulation and the nano observation. They sometimes walk and go on independently, and sometimes they cross. And when this happens, we have nice results, nice physics, which can be published, accepted in a Nature paper. Okay, so I'll talk about them separately, starting by the nano manipulation. And what I understand by nano manipulation are a set of operations that we do at the nanoscale, which modifies the properties of the matter. So, for example, here I have like an opaque and ugly sphere that, for instance, if we could do useful nanomanipulation here, we could transform this ugly sphere to a shiny, bright, and beautiful one. This is just an illustration. And how can we do expand this same idea to the nanotechnology? So by using the twisted bilayer graphene, which is frequently called by TBG and is also called by the magic material. Okay, to understand the twisted bilayer graphene, we should understand the graphene itself. So it is a very thin layer of carbon atoms arranged on a honeycomb structure like this one. But I'm not interested in the isolated graphene. I am interested on deposit one layer on top of each of one and rotating one of the layers. So we observe these beautiful structures, which are called Moire patterns. The distance between them is modulated by the angle according to this formula. In addition to this beautiful geometric structure, the properties of this TBG is also modulated by the twist angle, as I will show right now. But the graphene has this specific electronic structure composed by two direct cones, that totes, okay? And according to this structure, we can say that the graphene is a semi-metal. But when we go to a twisted bilayer graphene with large angles, okay, large angles here are angles larger than 5 degrees, we have not one, but two direct cones. And in the intersections between them, it forms some gaps which have optical activity. And according to this paper, the optical activity is modulated by the angle. So we can select the light in a very specific fashion with the angle. Okay, so from a semi-metal, the TBG is now a tunable photodetector. And the magic happens when we go down to a 1.1 degree, which is also called magic angle. So the researchers, Yuan Cao and Pablo Jarillo from MIT, they figured out that at this regime, the electronic structure abruptly changes. So I draw your attention here to the to the flat band, which is located here. And they also measured the resistance of TBG devices as a function of the temperature and carrier density, and they observed superconductivity and modulators DOMs. Okay, so from that result, many researchers were so excited about it because this diagram is very similar to the cuprates. But the graphene is a very simple system, while the cuprates are very complex. And the cuprates have very large temperature superconductivity. So if we could understand properly the graphene superconductivity, we could understand and model the cuprates superconductivity. In that way, we could develop and make and engineer some devices in order to increase the temperature of the superconductivity, maybe reaching the room temperature. So this was very exciting. And the TBG, as I said, behaves like superconductor and Mach insulator. On the other hand, this paper shows that in other electrostatic conditions, the magic angle twisted bilayer behaves as a ferromagnetic. Okay, so this is a very interesting material. And what happens when we go down to lower angles? So angles smaller than 1 degree. A very nice material shows up with nice physics that I will show later. But the main point here is to show that by merging two graphenes, which are semi-metal, in a nano cauldron, by warming it with twist and gate voltage, we made two semi-metals to become a superconductor, an insulator, a ferromagnetic, and this new material that I will show later. So the TBG is a very special system where the nanomanipulation is really good, is really applied in a very beautiful way. Okay, so some other researchers used the same pattern, the same engineering to do twist in other layered materials, and so a new area emerged, which is the twistronics. It is very fresh and new. Now that I talked about the nanomanipulation, I will talk about the nano observation. And before that, I would like to contextualize the size of things. And for that, I show here some scale bars where I divide in 3 realms, okay? And it measures the dimension of things from the matter. And in the macro realm, we are included on that. So we have from 1 meter to 2 meters. And ant is also included here, which has 1 centimeters of dimensions. And we go to the micro world, where the most famous element is the human cell, and finally to the exciting nano world. Okay, and a very terrible example of this realm is the coronavirus, which has about 100 of nanometers, and the fluorine, which is a really exciting material. And to observe each of these realms, we needed specific equipment. For example, the macro wall, our eyes takes account for it. So we can see almost everything in the macro wall. But when we go to the micro, we need an optical microscopy, okay? And what is the equipment? Which is the equipment that we can see and observe the nano wall properly? So that's a really good question and a very challenging problem. And to discuss that, I show here some equipments. I show in the x-axis the resolution that these techniques can attain. And I add the y-axis, which is the information that these techniques can provide you. So it varies from topology to functional information. The dielectric analysis is here at the macro wall, which can unravel only topology. But if we go, we walk on the x-axis, we find the STM and AFM techniques, which has nanometer resolution, but only shows topology information. If we go above, we find the electronic microscopy, which now unravels atomic and molecular information of the systems. And if we go back on the resolution, we find the ionic microscopy and X-ray. And going above again, we find the famous optical techniques as the IR, infrared, and Raman spectroscopy. So these are really nice techniques because it gives a very detailed information of the matter, but it is limited by the diffraction of light. So we can only go to 1 micrometer resolution. So there is a blank area here, which is in our case the nanoscopic, which couples the optical setups with the AFM. This is just a picture of our setup, of our nanoscopic here, and it is composed mainly by 2 sets of equipment. One set are composed by lens and objectives that will bring a light laser beam and focus it on our sample, on our TBG sample. And the other set is a very complex electronics, which will position a nano antenna on top of the light beam. Okay, so this nano antenna is the heart of the nanoscopic, because the nano antenna focuses the light on it on a very small point, which is about 10 nanometers. And just for reference, I plot here this red circle, which refers to laser spot, which is about 500 nanometers. So the nano antenna breaks the diffraction of light, and now we can observe optical phenomena at the nanoscale. And in addition to that, the nano antenna enhances all the optical properties of it. And the larger the enhancement, the better is the tip. We use special tips made here in Brazil now by our group and in partnership with Metro and Thiago, which we call plasmon tunable tip pyramids. This is a picture of it. So we have a true pyramid, and on top of it, we have a smaller pyramid here. And here's a picture of this special tip coupled to a tuning fork. To show you how powerful this nano antenna is, I show here the Raman spectra of graphene. In red is the standard spectra of graphene, and in blue is the spectra when the tip is down, so when the tip is in interaction with it. And we have these ultra large enhancements of the order of 100. And just for comparison, the standard commercial tips gives about 2 times of enhancement. Okay, and just for curiosity, my postdoc was part of a bigger project, including many scientists from engineering to information science, and they developed a commercial nanoscopic with Brazilian technology, and this is going to be sold very soon. Okay, and I'll go back to the physics, and I'd like to discuss a little bit about the optical spectroscopy. So it is the spectroscopy of the visible light, the light that we can see. And when the visible light is focused on a material, many physics happen, like absorption, radiation, refraction, many things. But I'm interested in the Raman spectroscopy. So in that case, we have, for example, a green light, a green laser with E0 energy. And when it interacts with the material, there is an inelastic scattering of the light. And so giving rise to 2 new photons or 2 new laser beams, which are represented by blue and red here. This blue one has a larger energy than the initial laser, so E0 plus EP, and the red one has a lower energy, E0 minus EP. And this EP is very specific for each material. It's like a fingerprint. And in addition to just a simple fingerprint, the Raman spectroscopy gives a very deep information on the materials. Like, for example, this is a very standard spectra from graphene, where we can see the D band is related to defects. We can see the peak from the substrate, and also the G band, which is related to this stretching vibration from the carbon atoms. Then we go to the 2D band, which is a second order process related to electronic structure stacking order, and also to this breathing phonon vibration. And we can also do images from these peaks. For example, we can do an image from the G intensity, and so we can map, we can see where our sample is, and we can see some details inside the sample. We can also make images from the G intensity, and we can see where in the sample there are defects. For example, here they are located at the edges. And we can finally plot the G width, which is related to the coupling between the electrons and phonons. So we can see where the electron phonon coupling is located at the space. Okay, so I will go now to some challenges that we find by trying to cross in the nano manipulation and nano observation paths. In the case of nano observation, we have commercial equipment, which is well established, so it's okay. But on the nano manipulation side, it's a little bit tough because it is really hard to precisely rotate one layer of graphene on top of each other. Okay, so this is not so easy, and we have other challenge, which is because when people nowadays prepare these TBG samples, they use a very thick boron nitride flake on top of it, which prevents our nano antenna to interact with graphene. So we need to get rid from this bulk HDN. And we developed a solution which was published here, and it is based on some pyramid stamps made from PDMS, which is kind of a silicon, and we can make them in a very controllable fashion and reproducible, large scale, and we can make pyramids with different sizes, like for example 150, 50, and 10. And now I'll show how we use these pyramid stamps to prepare twisted bilayer graphene samples, okay? So we use our pyramid stamp and cover it with a polycarbonate polymer, and we have our graphene here, which is on top of a substrate, which in turn is on top of a metallic base. And here's an optical image of our graphene flake and also the pyramid. So the next step is to align the pyramid edge to the middle of the graphene flake. This is just an optical picture showing this procedure. And then we engage, so we approach the pyramid stamp to the graphene sheet, and we do temperature increase. And by doing that and cooling it back, we cut the half of the graphene sheet. So one of the graphene sheet is located at the pyramid stamp, and the remaining piece is located at the base, so at the substrate. So this is the trick. We now have two graphene sheets which were also once one single sheet. So they are perfectly aligned, and we just need to rotate the base, and we can stack these two sheets, and we can form our TBG. So we stack them and pick the two pieces, which are here located at the pyramid stamps, and we have the TBG form. Okay, so this is an optical image, and we can transfer this TBG to every other substrate we desire. So, for example, we have here a graphene sample on top of silicon dioxide silicon wafer. Then we make a cut here, pick this piece, rotate the base, this guy here, and we stack them, pick them, and transfer to a cover slip, which is other substrate. And here we have a twisted bilayer, clean, really good sample with no boron nitride flake on top of it. So we solved all the issues to get nice results, and I'll show our results from our paper, which is localization of lattice dynamics in low angle twisted bilayer graphene. Okay, and one of the questions is what was so exciting about your results that you guys could publish on the cover? Okay, one of them behind it there is a question: what is this graphene's superconductivity origin? So Pablo Harilu himself and other groups believe that it is due to strong electronic correlation. Okay, so the electron strongly interacts and form this conventional superconductivity. And some STM works show that this strong correlation is localized at some specific sites, like the AA sites. Okay, but on the other hand, there is an alternative story. So some theorists show that there is a very strong electron phonocoupling at the magic angle graphene, and it's so strong that some exotic physics show up, like the Wally-Yaw-Taylor effect, and this guy could have some contribution on the superconductivity. However, there are no experimental background on TBG phonos so far, I mean the magic angle TBG. And for angles close to the magic angle or smaller, the lattice constant of the TBG is about 10 nanometers. So it is a nanoscale problem, which only a nanoscopic can deal with it properly. And now I show one of our first results. And here is an image of Moore patterns from an rTBG, using visible light. So this was the first time that someone could image a crystalline structure by using visible light. Okay, but that's just it. That's just an image that you guys got. No, remember that the Raman spectroscopy gives a very in-depth, detailed information of the sample. So behind this picture, we have nice physics. And there is another question. I showed you before that the Moore patterns is something like this. So we have some hexagonals here, while the image that we measure has some triangles. So something is confusing here. You may say that the nanoscopic is measuring wrongly, or that I'm messing up with some information here. Actually, when we have a very small angle, like this one, about 0.09 degrees, which is smaller than 1 degree, a new material shows up. So the TBG now becomes rTBG, which is reconstructed twisted bilayer graphene. To understand what this material is, I show some theory results from this paper. And these guys showed that below a critical angle of 1 degree, the TBG suffers a reconstruction process. So the carbon atoms, they rearrange looking for an energetically favorable configuration, which is these triangular domains, okay? Just like we observe experimentally, okay? And to have a better idea of what this rTBG is, I show here a cartoon showing the fine elements of it. So we have the black and gray triangles, which are different ways of stacking two graphene sheets, which are the AB and BA stacking domains. The green lines here, which are also called solitons, are composed by SP stacking lines, and the white balls here are referred to AA topological points. And this particular structure makes this system very special with special physics, as I will show right now. So first, I'd like to discuss the phonons from this system. And to start, I show here a phonon dispersion diagram evaluated by the group from Vincent Milnier. And they plotted here in red the dispersion for Bernal bilayer, which is the configuration where the angle between the two graphene layers is 0. And they also evaluated this dispersion for the rTBG of 1 degree approximately. And look that there is a splitting of the phonon branches here and here. And what do we see in our experiment? Remember that the nanoscopic gives spectroscopic information at the nanoscale. So here I show nanospectrum at the AA site, SP site in blue, and ABBA region in black. So these peaks are close to the G phonon, okay? And at the ABBA site, we only see the G band, only one peak. When we go to the AA site, we see a new peak showing up at the left of the G peak, which we name GR minus. But for the SP, we see another new peak at the right of the G peak that we call GR plus. And so look that these guys, they are similar to what the theoretists observed. And the similarities do not stop by here. And here
He froze, right?
Yeah, he froze.
I stopped here.
You were describing the features on your results, the image that comes next.
Okay, here.
There. Mm-hmm.
Okay, so at the experimental side, we saw a single Lorentzian G peak at the ABBA sites, while at the AA site we observed a new peak at the left of the G peak, which we call GR minus, and at the SP site we observed another new peak at the right of the G band, which we call GR plus. Okay, so there is some similarity. There are some similarity between these experimental peaks and what the theorists observed at their diagram. Okay, and I now show the phonons in space. So the theory says that the GR minus mode. So here they plot the Raman intensity expected for this mode. The intensity varies a lot at this space. So they observe larger values at the AA sites. Like the experiment. So at the experiment, we plot the GR minus contribution peak over the space, and we see large intensities at the AA sites, like the theory observed. And for the GR plus mode, both the theory and experiment says that we have large intensities at the SP solitons. Okay, so both the theory and experiment are in agreement, and they elaborate that these new peaks that we observe and measure modulates over the space. So they have different intensities across the space. So this gives rise to a new concept, which is phonolocalization. Okay, we can also investigate electrons through the 2D band. Okay, so the shape of the 2D band is related to the electronic structure and other features as well. And here I show the local spectrum at the ABBA site from the rTBG. And those from you that are experts on the Raman spectroscopy of graphene may say that this is very similar to the Bernal bilayer. Well, that's true. And when we plot the contribution from this spectrum over the space, we observe larger intensities at the ABBA sites, which are like Bernal bilayers. And what we saw new here was the first spectrum from measured at the SPAA region. And look, that it is very different than the previous one. I have never seen this kind of shape before. And when we use this spectrum to map the space, we observe stronger intensities at the AA and SP points as expected. So these results tell me that the shape of the 2D band varies through the space. So we can say that we observe electron localization, so the electronic structure is varying through the space. And as we investigated electron and also phonons, why can we not investigate the electron phonon coupling? We can do that by measuring the U width, so the full width at the maximum. It is a parameter related to the electron phonon coupling. And here we show a map from this parameter, and we see some modulations over the space, and we observe higher intensities at the AA site and smaller at the ABBA. To understand this, we need to look at the electronic structure close to the Fermi level, where G phonons can be observed generating electron-hole pairs, and we can say that the G phonon is coupling to the electron. And the larger the phonon absorption, the smaller is the phonon lifetime. And from the uncertainty relation from Heisenberg, we can tell that the phonon line width increase. And when the phonon line width increase, the electron phonon coupling increase as well. And this is just a simple picture. And we asked our collaborators from Jean Charlier Group to calculate the local electronic density of states for the rTBG at the AA, SP, and ABBA sites. And I marked here a region in gray where G phonons can mediate excitations and can do transitions, okay? And look that at the AA side, we have a very pronounced peak, and at the SP, we have two smaller peaks, and at the ABBA, we have no peaks. So this tells us that the probability for phonal absorption is higher at the AA and then the SP sites, just like we observed experimentally. So the higher the phonal absorption, the higher is the phonal width. Okay.
Just to clarify, these are theoretical results in the middle. Right?
Sorry.
This density of states is theoretical, right?
Yeah. And when we compare to what people observed before, so this is an STM measurement, and it tells us that the electronic density of states is higher at the AA sites. And here we are showing that the electron phonal coupling is also higher at the AA sites, okay? And in addition to that, the electron phonal coupling also suffers from localization effects. And to summarize what we observed in a basic physics fashion, I'd like to review some matter structures, okay? And I start by the atoms, which are the simpler structure in the matter. And it has an electronic structure which is kind of simple and is discrete. So we can count them, 1, 2, 3. And when these atoms arrange in molecules, we have a more complex electronic structures which forms orbitals, and they also have the discrete behavior, like we can count 1, 2, 3, just like the normal modes, which are vibrations that we can count. So 1, 2, 3. When we go to crystal, this is different. So the energy and the phonal behavior is now continuous, not discrete anymore, and they form bands. One interesting result about crystal is that they have translation symmetry. So all the properties from the crystal at some point is very similar to the properties of the crystal at the other point, if the crystal is perfect. But in our case, so we investigated the rTBG, which is kind of a crystal. It is a super crystal. But here, the properties varies in this space. So the properties in the red point is different than the black region. So this crystal looks like atoms in molecules. And we can include here in our nano-manipulation story a crystal that behaves like atoms and molecules. Okay, guys, so I'm finishing my presentation, and now I'm going beyond the nano wall. So going back to the micro wall, because the nanoscopic is hard, and is not everyone has this equipment, but almost everyone has a Raman microscopy. And so we are looking for a fingerprint for the rTBG at the microscope realm. So here we plot the G width as a function of the twist angle in blue, and in red we plot the Bernal and single layer for reference. And for decreasing the angle, we see that the G width increases, reaching a maximum, and below that, the G decreases, width decreases. Reaching value is close to the Bernal bilayer. So this is a Raman fingerprint. So you guys, everyone can use this diagram to calibrate the angle of your TBG. So you prepare the TBG, and once you know the angle, you can check it here. Okay. And interestingly, this maximum value is close to 1.1 degree, which is the magic angle. So it may tell us that the electron phonal coupling related to the G width is stronger for the magic angle twisted bilayer graphene. So we are trying to investigate this further, and we believe we are going to get nice results on this topic. So as a conclusion, this is more like a perspective. So my dream as a researcher from nanotechnology is that in the future we have such control over the matter that we can do observations and manipulations at the same time. For example, in a DNA which has a defective genome, we can probably observe it and fix it and replace it. So this is my dream as a researcher, and I hope that our results help this dream to occur. And I'd like to thank you guys for the audience. I'm sorry for this problem. And I'd like to thank Christian and Adrian specifically, and Professor Aldo, and all the nice collaborators that we have during this project. Thank you very much. And let's go to the questions. I'm glad to talk to you and to reply your questions.
Thank you, Andreij. So now we have time for questions. Anyone who have a question, please ask. I think you can unmute yourself. Let me just double. Yes, you are allowed to unmute yourself.
Okay, Andreij, can you hear me?
Yes, I can hear you.
Ok, obrigado pela apresentação. I was just wondering about this tiny angle twisted bilayer structure of 0.09. There was a proposal some time ago that if you go to slightly higher energies, you would find bands that form not a triangular structure, but a Kagome structure. You know, did you verify this?
You mean this kind of work is for twisted bilayer graphene or for other structures?
Yeah, it's for tiny angle twisted bilayer graphene.
Yeah. We didn't see this. We only saw triangular geometries below 1 degree. But for angles larger than 1 degree, we saw some nice results on S-mean, which is another alternative technique in collaboration with Gilberto. So we saw very different structures here. This is some example. Can you see?
Yep.
So yeah, we saw very different structures above the reconstruction, but below the reconstruction, we only saw triangular fashions.
Okay.
I saw something like you mentioned for I saw a work, but with TMDs. Okay, they saw different structures.
Yeah, there is these proposals in TMIGs, but I think the first work which proposed something like this was in twisted bilayer graphene. So, but it was theoretical, so maybe it was not present anyway. Second thing, do you know if this nanoscope can be used to probe magnetic excitations if they are, you know, magnetic excitations if they are present in your material, or is it only phonon excitations that would be allowed to be probed?
Yeah, I don't know if we can probe magnetic excitation with this special tip because it has no magnetic material on it. We could try to probe some Raman bands which are related to magnetism. There are some reports on 2D magnetics on it. So at first we could do that, but we could in future also implement some magnetic alloy with gold that could directly probe these magnetic properties. But this is just some plans for the future.
Okay.
At the beginning of my work, I was trying to investigate this, but everybody said that it was really hard to do, and I just gave up.
Okay. Don't worry. Thanks.
Thank you for your questions.
Any other question?
So here is one question. Can you go back to your 2D mapping of the nanorama imaging?
Yeah, sure. I'll go on here. This one?
Yeah, here. So here I saw that the intensity seems to changes from the bottom, from the left bottom corner to the right top. So there is seems a gradient. Do you know why?
Okay, this is a problem of misalignment between the tip and the focus. So this image takes about 1 hour to finish. As we during the recording process, the tip starts to thermally drift, okay, from the laser, and we have this this enhancement decrease, okay. So this is a problem for the intensity signal, but this would not mess up with the other analysis, like they do with the intensity ratio between the 2D and G bands, okay? This would not mess up, but the intensity decrease is frequently observed in near field systems, okay? Especially in our case that we do spectroscopy. So we record the spectra, which sometimes take a long time, for about 1 second. And so the thermal drifts are unavoidable.
I see. The other question is like, how does the light shine to the tip? Is from the side or is from the bottom?
Okay, good question. The light in our setup is from the bottom. So the reason we do this, let me see if I can take. The reason that we do this is because this nano antenna work as a collector of light. So this guy works as a plasmonic cavity, and so when we put light laser from the below, this guy enhances even more. Okay, so we need to work on the I forgot the name, but on the radial polarization. Okay, so with very high NEA apertures, so we can work on the polarization light perpendicular to parallel to the antenna. Okay, and we could use side illumination and tilting the tip, but this condition that laser focuses on all this trunk is really good to have these ultra large enhancements.
Yeah. Yes. If you shine from the side, maybe the tip won't see the light.
Yeah.
Okay, very good. Thank you very much.
Thank you for your pertinent questions.
Let's call for questions. No, if there is no questions, thank you very much, Andreij, for being with us. We apologize for the technical glitch. I hope to see you all next week. Thank you, Andreij. Thank you, everyone.
Thank you, Adrian, and thank you, everyone, for being watching my presentation. See you. Be safe.